Hi, in this video on experimental research, we're going to talk about the differences between random selection and random assignment and why they are so important in allowing experimental research to determine cause and effect relationships. So we're going to talk about how we select our research participants. Before we do that, let's cover a little bit of vocabulary that's important to understand, the difference between a sample and a population. So a population is going to include all individuals of interest. Well, the representative sample would be the people that you run the experiment on. So again, the population is going to be all individuals of interest. Maybe our population will be all community college students or all low-income preschool children. Now that could be very large and also vary in size. But if you think about all community college students in California, that would be a really large number and a little too daunting to conduct your experiment on. We want the results of our study to generalize to the population, so we want a representative sample. So a representative sample is going to be selected from the population of interest, whether that's community college students, low-income preschool students, Democrats, whatever it is. Your sample is selected and selected in such a way so that they represent the population in a research study. And so we're going to talk about in this video how you get that representative sample and then how you assign that representative sample to your different groups in the experiment. So just to reiterate, the reason why we use a representative sample and not the population is because that population would just be too large. So an example might be students at Orange Coast College or, like I said, college students in California. So that would be too many. So we want to get a representative sample, and maybe that's just Professor Ferguson's class. Because think about all of these things, how all of these different people in this population can differ based on socioeconomic status. You see here hair color, age, sex, educational background. And so when we pick this sample, we want it to be representative. And to do that, we're going to use something called random sampling or random selection. So the question is how do we get this representative sample? And the hallmark is something called simple random sampling. I'll also refer to it as random selection. So this is where participants are selected from a list containing the entire population. This ensures equality so that each individual has an equal chance of being selected. It also has independence. This is where the choice of one individual doesn't influence or bias the probability of choosing another. So that's the idea with this simple random sampling. And there are a variety of different types of sampling techniques. You go on and take an experimental methods class or another class in psychology, and you'll learn more details. But for this, we're just going to simply call it simple random sampling, or also refer to it as random selection. So the steps for simple random sampling or random selection are quite simple. First, we're going to define the population from which you want to select the sample. You're going to list all members of the population, and then you're going to use a random process to select that population. And for an example, we're going to use a study that I worked on as an undergraduate called Project Primer. The researchers wanted to see if early interventions help with cognitive outcomes in elementary school children that came from a low-income background. So the population of interest was the youngest siblings of Head Start families in Southern California. We gathered a list of all members of our population, that was our sampling frame, and then we used a random process to select individuals. So here is our list of Head Start families in Los Angeles, and this is a fictitious list. Typically your sampling frame wouldn't have gender and age listed, but I have it here for demonstration purposes. Typically your population will be much larger than this. Think of it being 10 times the size of this. But again, for demonstration purposes, I've had to limit it so we can see everything on the screen. So we have 100 families here. Think of, an actual population being 1,000 or 10,000. And our sample size, which is predetermined, is going to be 25. Imagine adding a 0 to that for a real study. So using the random function Excel, I've selected 25 participants. So there's a function in Excel. This list of names was in Excel. I used that and it randomly selected 25 names from that. So here I've listed those 25 names of randomly selected participants. And let's compare now the statistics between the population and the sample. So here was my population originally. Again, it was fictitious, so it was pretty perfect. 50% male, 50% female, and then 34, 33, and 33 of age 1, 2, and 3-year-olds. Because again, remember, these are the youngest siblings of Head Start children. So when I randomly selected my sample using simple random sampling, the random function in Excel, I ended up with 56% male, 44% female, and 36, 32, 32 of 1, 2, and 3-year-olds. That's pretty darn close. The sample generalizes to the population. These background characteristics that are important, remember we're talking about cognitive outcomes, right? So the cognitive abilities of a 1-year-old are very different than that of a 3-year-old. So we want those ages to be representative. If not, that could skew our results. So because our sample generalizes to the population, we have something called external validity. It's going outside of our sample. We can generalize those results beyond because of that external validity. Now, what happens if I don't use random selection? Or simple random sampling. Let's say my sampling frame, my list, is listed in terms of age, but I'm being lazy, and instead of using a random function in Excel, I decide I'm just going to pick the first 25 names. So here I've just picked the first 25 names, and you can see that the sample is only comprised of 1-year-olds, not nearly representative if we want to compare, if we want our sample to represent 1, 2, and 3-year-olds. So you can see here a reminder that our population had 1/3 each of 1, 2, and 3-year-olds, where our sample only has 1-year-olds. So those results aren't going to generalize to our population of interest. If we were interested in only 1-year-olds, sure, but we're interested in 1, 2, and 3-year-olds, these younger siblings of Head Start families. We're not just interested in the 1-year-olds. So the sample is not representative of the population. It makes it difficult to generalize those results. Now that we have our sample, we need to assign those to our groups. So in this Project Primer study, we actually had 3 groups, but for the sake of demonstration, we're just going to do 2. Let's say we had a control group that did not get any intervention, and then we had an experimental group where we went out to the families 16 times throughout the year, and we took books and other supplies, and we worked on a concept with those families at that visit. And we were enabling the parents to be able to do those activities with the children in between our visits. And so the books had some sort of concept, whether it was colors or numbers or shapes, and then we had a game and a song that went along with that. And so we wanted to make sure that that sample, that representative sample, is equally distributed in those 2 groups so that those groups can be compared. So random assignment uses the same type of random tools as simple random sampling, a random number table, a computer program, pulling names out of a hat, a coin toss, something to randomize the sampling. Evenly distributes the background variables among the groups. So again, here in our example, we're interested in things like gender and age, but maybe in another study, it might be socioeconomic status, amount of schooling, intelligence level. There's a variety of different things. So again, using random assignment is going to allow experimenters to make statements about cause and effect relationships. So it's the 2 important things for an experiment to allow the determination of cause and effect relationships are that manipulation of the independent variable, and then using random assignment to assign groups to those different conditions. So making those cause and effect determinations is that primary goal of research. So let's talk about the benefits of using random assignment. So here's my representative sample that we got using random selection or simple random sampling. Again, gender and age may not necessarily be listed, but I have it here for demonstration purposes. I again used the random function in Excel and randomly assigned the individuals 1 or a 2, 1 being in the experimental or the control group and 2 being the experimental group. And let's compare our statistics. So group 1, my control group, we have about 36.4 and 63.5% females, and then 45.4, 27.3, and 27.3 in the different age groups. My experimental group is 50-50 male-female, and age 1, 2, and 3, 28.6, 35.7, and 35.7 respectively. So they're not perfect, but it's random and it's representative. And if I was to do it again, I would get a different percentage. But the idea of using random assignment is that it helps distribute those background characteristics between the two groups. And of course, the larger the sample, the better your distribution is going to be. So groups are similar to each other. That gives me internal validity. So within the experiment, I have validity. I can know that the results of my experiment aren't due to gross differences in the ages between my control group and my experimental group. So what if we don't use random assignment? So here, let's just say my representative sample is listed in terms of age, and I'm being lazy again, and instead of using the random number function in Excel or pulling names out of a hat or flipping a coin, I decide I'm just going to take the first half and put them in group 1 and the others in group 2. So, and you can already see just by looking at this, that means I'm going to have 1 and 2-year-olds in group 1 and 2 and 3-year-olds in group 2. So here are the male and female again. Group 2 might not be as representative as we'd like, but it's randomness. But when we look down here, this is the big difference. In group 1, we only have 1 and 2-year-olds, and in group 2, we only have 2 and 3-year-olds. And if group 2 is my experimental group, and they're getting the intervention, and I'm going to look at cognitive outcomes, not just immediately after the experiment's done, but in the future at age 7 or 8, now I'm going to see immediately, I'm going to probably see cognitive differences between my control group and experimental group just based on age, right? 2 and 3-year-olds overall are going to be more cognitively advanced than 1 and 2-year-olds. And by what I mean by cognitive advancement is, maybe the number of shapes that they know, or the number of words that they can recognize or say. So in that frame, that they are going to be more advanced. And so I don't know if differences that I see are due to the manipulation of the independent variable or differences in my two groups. Groups are not similar. It's difficult to determine causality. So just a comparison of random selection versus random assignment. So in random selection, every member of a population has an equal chance of being selected for the sample. In random assignment, every member of the sample has an equal chance of being placed in experimental or control groups. Background characteristics in random selection, we want them to be similar in the sample and the population. So we want a representative sample. In random assignment, we also want those background characteristics to be similar, but we're now looking at the experimental and the control groups. Random selection gives us external validity, and random assignment gives us internal validity. So let's go back and go over our example using vocabulary that we've been talking about in several videos. So our hypothesis is that early literacy intervention would improve emergent literacy in low-income children. So we're predicting that literacy intervention, going out to the houses, bringing books, enabling the parents to help, read with the children and play games and sing songs, would improve emergent literacy, which is basic, simple cognitive outcomes like the number of words they knew, the shapes they know, the colors they recognize in low-income children. That's our population of interest. So our population was Head Start families. We used random selection to get our representative sample. We then used random assignment to put them into our control and experimental group. The control group got no literacy intervention. The experimental group got the literacy intervention. So that was our independent variable. That's what we manipulated. We then gave them a test of language comprehension and cognition before and after for both groups. And we compared those scores. That was our dependent variable. We again predicted that the manipulation of the independent variable would have an effect on that dependent variable. And then we performed statistics to see what the differences were.